All right, guys, welcome back to Introduction to Automation and Programming for the IT Professional. We're going to be talking about sensing the world. And so, chapter 4 is all about sensors. So, we've been doing a lot of things with digital technologies, and this is where we're going to start branching into analog technologies. So, nothing is going to be black and white in the real world. Digital is great, but all we get is zeros and ones. But what if we want to control things that are not just zeros and ones? What if we want to look at temperatures? What if we want to dim an LED by a certain percentage? Maybe we want to do something, well, not 100% all the time. For instance, I don't want to run the motor at 100% or no percent. I want to be able to control the motor speed on my devices. So this is where we're going to introduce analog. So many sensors produce analog voltage, and that varies constantly. So all the microcontrollers themselves, while they're digital devices, they don't understand what analog voltage is. So if you remember back in chapter 2, we talked about analog being more of a sine wave. Instead of it being a digital wave of either on or off, we are now talking about, well, a sine wave. We're talking about anything in between. Instead of 5 volts, maybe it's 3.3 or 3.2 or 2 or 2.1 or 5 or 0. It's everything in between. So analog is that special type of technology that's going to help bridge the gap between digital and analog. Inside of our Arduinos and our ESP32s and all of our microcontrollers today, we have what's called an ADC. It's an analog to digital converter. Now, this is going to be the bridge between the analog and the analog physical world and the digital microcontroller world. Its job is to measure analog voltage and convert it into a numerical value. Now, remember, we were talking about how analogs in chapter 2 are always between 0 and 1023. Well, 0 and 1023 is great, but what if we're talking about temperature? Well, what's going to happen is that sensor is going to come back with a voltage, and then we're going to read that voltage and convert it into a calibrated number that actually makes sense to us. Maybe that means 72 degrees in our house. So the microcontroller on the Arduino Uno is a 10-bit ADC. So 10-bit means it represents voltage by 2 to the 10th power. And this number may look very, very familiar at this point, because 2 to the 10th power is 1024. So that's 0 to 1023. We have 0 to 123 distinct digital levels. Now, what does this mean? Well, if I see 0 volts, the digital value is 0. But if I see the max voltage of 5 volts, well, the digital value is going to be 1023. So what would be 2.5 volts? Well, if we look at that, we'd say, well, that's about half. So we should see it around 511, 512. So that's what we were going to see with that conversion. So if I got a value from a sensor that says 511, then I know that it's 2.5 volts. But that not everything's going to be voltage, and not everything's going to just be a number. And so we need to have some way of mapping that number back to some realistic value. Now on the Arduino Uno, there's special pins that are allowed to do analog. Okay? By default, it's the ones that start with A for alpha. Okay? A for analog. And so if you look at your Arduino, you'll notice that it has an A0 through an A5. These pins are designed to be analog. These are not digital pins. So if you want to use an analog device, you should connect one of your devices up to one of these analog pins. Okay? Now, instead of digital read and digital write, we are now going to change our logic to analog read and analog write. For instance, if I have something connected to A0 on my Arduino and I want to read the value, I will do an analog read of A0 and I would store it into a variable. Now, these are whole numbers, 0 to 1023, so I can use an integer and store it into a variable called sensor value. So every time I read this sensor, I can store it into a variable, which then I can then logically do if statements, for statements, while statements, and do things to that variable, or even use it to print data to the screen. Now, if I want to convert this signal over, you can always approximate the voltage by a simple calculation. You take the sensor value and you multiply it by 5 over 1023. And a lot of people are like, well, why 5? Well, it's because the Arduino power is at 5 volts. It runs off your USB port, and it's designed to output 5 volts on each one of the pins. So if you use a different microcontroller, this 5 could change to a different number, but it's always going to be that number, the voltage, divided by 1023. Now this will give us the voltage that we see on that line. For instance, if I got a number of 511 and I wanted to know what voltage that was, 511 times 5 divided by 1023 is going to be 2.5. That's how we can determine how much voltage is within a single pin. Now, how do we control our analog signals? Well, we can use what's called a potentiometer. And you've used potentiometers every day. You've heard me say this before. For instance, you used a potentiometer when you go into your car and you turn the volume up and down in your car. That is a potentiometer. Depending on how much you turn the knob to the right, it turns up the voltage on the signal to the speakers. The higher the voltage, the louder the sound. The lower the voltage, the lower the sound. So a potentiometer is just a variable resistor. Instead of putting a resistor in front of my LED and having it turn on an LED, maybe I put a potentiometer instead. This way I can control it. Now, just be aware, we still have a max voltage on our devices, and we do not want to let out the magic blue smoke. So if the device is designed to run between a certain voltage, make sure we don't go above that voltage, okay? So we may still want to use a resistor, like a 220 ohm resistor in front of our LED, to ensure that we do not blow out our LEDs. Okay. Now, how do we wire in a potentiometer? There's always going to be the outer pin. It's normally either a 5 volt or a 3.3 volt, depending on the potentiometer. There's always going to be a ground pin. And then there's always the wiper pin. Now, the wiper pin is whatever is coming in for the Arduino itself. So think of this as A0. Now, between the ground, the 5 volt, and the A0, then now we can read A0, and as you turn up and down that potentiometer, you'll see a value between 0 and 1023. So we can actually see the value go up or down. And we can utilize this in other labs, and we will in the future. But just be aware, if we wanted to control the LED brightness and use like a dimmer switch, I would then set the LED as 1 and then set a potentiometer for the other. So that way I can set up my LED between 0 and 1023. I will then have a dimmer switch. Now, there are going to be a lot of ways, a lot of different types of sensors we can use. And so in our kits, there are a ton of different sensors, okay? And so we'll go through a couple of what some of those look like. Because some of them do light, some of them do heat. It all depends. For instance, light. We have a photoresistor inside of our kits. The photoresistor itself has a little squiggly line on the top, has a little cell in it. And so if you're looking the text document for this chapter, there's a picture of what this looks like, or you can always look back at the appendix of the book itself, which there's even more pictures back there about photoresistors. So the more light, the lower the resistance. Basically, the more light, then do we turn on or off an LED. And you'll see this a lot in like houses where if the light is on in the house, it doesn't turn on the lights. But the moment the light turns off, it turns on the lights. And this is using a photoresistor to complete this for you. Now, how do we do it? Well, it's an analog read. Now, it measures voltage, not resistance, and then you can read that voltage and then utilize it For instance, remember, analog read is always going to be between 0 and 1023. And I hope me saying it 15 times over is getting you to realize it's 0 to 1023. That's how all analog devices are going to read, especially when it's 2 to the 10th power. Now, another sensor that we may use might be like a TMP36 or a DHT11. I believe we have those in our kits, or 22s we have in our kits. Now, depending on which type of circuit it is depending on what we're going to use. Now, these are temperature sensors, okay? Now, the one that's in our kit actually is a temperature and a humidity sensor, so it goes above and beyond. But just think of this, TMP36 sensor is still an analog device. It's still going to read something, give it back to us as 1023, and then we're going to convert it into either degrees or Celsius or anything like that. Now, make sure that you connect it correctly. If you connect it backwards, it will permanently damage it, okay? So double check, triple check your circuit before you turn this one on. Make sure that you have positive and positive, negative and negative, and that the signal pin is actually going to the proper A0 to A5 pin on the Arduino. But reading all this information directly to the Arduino isn't going to do us any good. So how are we going to get that information somewhere else? So what we're going to use is serial communication. So we already had that question before. What do we use? We use the serial monitor. Well, we're going to use that serial monitor, but we have to be able to use serial communication within our network in order for this to work. So it's going to send us text-based messages from our Arduino over the USB cable. So it's going to send it to us 1 bit at a time. Serial communication means we're going to get 1 bit at a time in a line. That's why we call it USB, Universal Serial Bus. The Arduino Uno uses its hardware pins 0 and 1 to receive and send. Now, this information will be transferred into the USB interface chip. That way we can communicate to it. This is also why the Arduino is connected to our USB port and it shows up as a COM port. Now, how fast can we communicate? It depends. The Arduino doesn't run very fast. We will communicate with the Arduino with a common baud rate of 9600. 9600 bits per second. Still a lot if you ask me. While this is very slow in today's communications, 9600 bits per second is way faster than what I can read. But this is where we're going to see the connectivity. Now, the beauty of this is the Arduino IDE already takes care of this for you. By connecting to the COM port and picking the board, it already knows what baud rate it can communicate with. But if we were going to use a different tool like PuTTY or MOBA Xterm or one of the other programs that talk with serial communication, we would then have to also configure the serial baud rate. Now, in order for us to start this communication, we need to use the serial object. We've seen this before in a different example where we did serial.begin. And we put this in our setup method. Serial begin, and what speed do we want to talk at? Okay. We want to put this in our setup method because it's a one-time only pickup. If for some reason we drop this, in order to bring it back, we would have to unplug the Arduino and plug it back in. Now, if we want to print the data to the screen, to our serial monitor, we would then use serial.print or serial.println. Serial.print says print this to the screen, but do not move to the next line. Serial.println says print to the screen and then go to a new line character. A lot of times if you're only printing text to a screen, like the temperature, you're going to use serial.println. We'll be using that in our lab. In Arduino, the built-in tool is called Serial Monitor. So if you go to Tools, Serial Monitor, you'll see it at the bottom of the screen. And any communication that happens between the Arduino and us, we will see displayed there. So if we did a serial.print and we were looking for the printout of the serial communication, we need to look there for that communication. The critical step is we need to make sure that we're talking the same speed as our Arduino. If we don't match the same speed, you'll see a whole bunch of garbage characters or nothing at all. It just isn't very good. Okay, so make sure that if you are using another tool, that we are all talking at the same speed. All right, so in today's lab 4.1, we're going to bring this all together. It's going to wire in a photoresistor and a TPM36. These analog values will then come back to us as a serial monitor. This way we can actually read in. Just be aware that the TMP36 sensor may need to be changed out to whatever sensor's in your kit. The TPM36 TMP, I keep saying it, TMP TEMP36 sensor is a generic sensor. We may have other sensors in there. So keep an eye on that, and if it is a different sensor, try to read the sensor. Try to see if it's hooked up differently. Make sure the pins are set up right. Because remember, some of these do not like to be hooked up wrong. And if you do hook it up wrong, you might break it. Okay? So be very extra careful with this lab, so that way you can get something cool out of it and understand how input devices work throughout our systems. All right, so this is our introduction to analogs. We're gonna be talking. We talked about potentiometers. We talked about light detection. We talked about temperature sensors. Talked a little bit about how do we get that information back to us, like through serial communication. And when we go through this project, try to keep those in mind of how could you utilize this in the real world. How could you use this as an IT professional? I can think of a few different ideas, but I would love to hear what you guys think. All right, I'll see you for Chapter 5. See you next time.